Welcome back to the Deep Dive. Today, we're taking a serious plunge into one of the biggest intellectual earthquakes in history. We're charting the journey from the ancient universe, as seen by someone like Aristotle, all the way to the mechanical, predictable cosmos laid bare by Isaac Newton.
Yeah, and it's a story that didn't just, add to our knowledge. It fundamentally reshaped how we thought about reality itself.
How we thought about everything, really.
Right. What the world is made of, how things move, and whether the heavens are really all that different from the earth under your feet.
And we've got this stack of sources here covering exactly that shift the ideas, the figures, the moments that built the bridge from one titan of physics to the next.
Our goal for you today is to slice through all this material and pull out the absolute most important nuggets.
Right.
We want you to grasp how our view of nature was turned upside down and what exactly made Newton's big synthesis so uniquely powerful and honestly a little bit mind-bending.
Okay, let's start at the beginning of our story, which is really the end of a very long era, Aristotle's universe. It stood for centuries, built on what seemed like two pretty solid pillars at first glance. What was the world made of, and how did it change?
That's right. For Aristotle, there was this fundamental divide. Everything on Earth was composed of four basic elements: earth, water, air, and fire.
The classics.
Exactly. These were seen as corruptible, subject to change and decay. But look up at the heavens. Completely different story.
Oh, yeah.
That realm was made of a perfect, unchanging fifth element, the ether.
Ether. Okay. So different stuff up there than down here. And that applied to movement, too.
Absolutely. On Earth, you had two main types of change.
Right.
Things transforming qualitatively, like water turning to steam,
Okay.
and things moving in a straight line, like a rock falling.
Wow.
And crucially, for Aristotle, that motion required a continuous push or pull.
You had to keep pushing it.
Right. Stop the force, stop the motion. But in the heavens, movement was eternal, perfect, and circular, the only fitting motion for perfect ether. The distinction couldn't be starker.
But this picture, while, elegant, started to get complicated over time, especially as people looked more closely at the sky.
Exactly. The movement of planets isn't simple uniform circles. You see things like retrograde motion, where a planet seems to loop backward.
It goes the wrong way for a bit.
Right. Explaining this within the pure Aristotelian model required adding layers and layers of complexity, like Ptolemy's epicycles.
Circles on circles.
Yeah, they worked mathematically to predict the motion, but they felt increasingly clunky as a description of physical reality. This complexity was a huge crack that eventually led to Copernicus suggesting, maybe the sun's at the center.
And down on Earth, the idea that motion needed a constant force didn't always ring true either.
Think about throwing that rock again. You give it a push, and it keeps going through the air even after your hand has let go. If motion required a continuous force, what was providing it after it left your hand?
Good question.
Aristotle had explanations involving the air pushing the stone, but they felt forced, a bit Rube Goldberg-esque.
A bit contrived.
Yeah. This highlighted the need for something like an internal motive force, which thinkers like Ibn Sina in the Islamic world explored, or eventually the concept of inertia.
So these challenges, they really paved the way for the next big wave, starting with the Copernican revolution. Putting the sun at the center seemed like just an astronomical shift, but the sources show it was a profound philosophical one.
Oh, completely. Suddenly, the Earth wasn't special, not the fixed, unique center. It was just another planet orbiting a star.
Just one of the planets.
Right. Which meant Earth and the heavens weren't fundamentally different places made of different stuff with different rules. They were part of the same system.
And that opened up some incredible possibilities.
For one, the sophisticated mathematics that had been developed to describe the precise, perfect motions of the heavens could now potentially be applied to the messy, imperfect motions down here on Earth. The math could unify the two realms.
So the same equations for planets might work for falling objects, like an apple, maybe.
Precisely the hope. Also, with the Earth itself now spinning and orbiting, the whole concept of motion became relative.
Relative to what?
Exactly. Moving relative to what? That question became unavoidable. And most importantly for our story, the realization that Earth and heavens were connected provided a huge motivation to find a single, unifying physical reason for all motion everywhere.
And that search involved some brilliant minds who built crucial pieces before Newton.
Absolutely essential figures. You have Johannes Kepler,
Kepler.
who took Tycho Brahe's painstaking, precise astronomical data and found mathematical order. He replaced Aristotle's circles with ellipses and gave us 3 laws describing how the planets moved.
Just describing how.
Purely descriptive, kinematic laws, but incredibly accurate.
Then Galileo Galilei focused more on earthly motion.
Galileo was the experimenter, the one who idealized situations to uncover fundamental truths. He gave us accurate descriptions of things like projectile paths.
The cannonball trajectory.
Right. And crucially, studied freefall, showing that objects fall with constant acceleration regardless of their weight, ignoring air resistance.
Big insight.
Huge. He championed the concept of inertia, that tendency of an object to resist changes in its state of motion, and explored the relativity of motion.
And Descartes provided a whole new philosophy of nature.
Descartes envisioned a purely mechanical universe. Everything was just matter in motion.
Like clockwork.
Pretty much. Interacting only through contact. He proposed principles like the conservation of matter and the conservation of what he called quantity of motion, which is essentially momentum.
And his math.
Oh yeah, his invention of analytic geometry gave everyone the mathematical language to describe motion precisely. Super important.
And Christian Huygens, who was incredibly close to some of Newton's key ideas.
Huygens was a powerhouse of 17th century physics and mathematics. He did crucial work on pendulum motion, and, significantly, was the first to correctly analyze circular motion.
The force needed to go in a circle.
Exactly, and derived the formula for the force directed towards the center, the centripetal force. He rigorously formulated conservation laws.
So close to Newton.
Some sources suggest he had many pieces of the puzzle Newton solved, but perhaps his deep commitment to Descartes' contact-based mechanical philosophy.
No action at a distance for him.
Right. That might have prevented him from accepting action at a distance, which was necessary for Newton's gravity.
Okay, so while these thinkers were revolutionizing how things moved, there was also that other pillar of Aristotle's physics, crumbling the idea of what matter was made of.
Right, the elements.
Yeah.
Aristotle's 4-element theory was about qualitative properties, hot, cold, wet, dry, determining substance.
Uh-huh.
But the idea of matter being made of tiny, indivisible particles, atoms, was ancient, going back to Democritus.
Atoms, way back then.
Yeah. His was a purely mechanical reductionist view. Different properties arose simply from the shape, size, and arrangement of atoms moving in empty space.
A direct contrast to Aristotle.
Exactly. Democritus's idea was philosophical, not based on experiment, and it was sidelined for centuries, but it persisted as an alternative way of thinking about matter.
And Aristotle's elements faced their own problems over time.
Well, how did fire turn into air? The mechanism for element change wasn't clear.
Yeah, how did that work?
And thinkers like the Stoics questioned the need for 4 elements if they could just transform into one another. The system of assigning qualities felt a bit arbitrary and didn't really explain things deeply or allow for quantitative prediction.
The real challenge came from people actually doing chemistry.
Yes. Systematic experimentation, which saw significant development in the Islamic world with figures like Jabir ibn Hayyan and Al-Razi, and later in Europe.
What did they find?
They revealed a world of substances far more complex than 4 elements could account for. They found substances with properties not reducible to just hot, cold, wet, dry.
And the very idea of empty space, which Aristotle rejected, was tested.
Crucially challenged by Evangelista Torricelli in the 1640s, his experiment with a tube of mercury creating a vacuum above the column.
The barometer.
Right. It was empirical evidence against Aristotle's idea that nature abhors a vacuum. This demonstration of empty space was vital for a particle view where atoms move in a void.
And then Robert Boyle brought it all together in chemistry.
Boyle's The Skeptical Chemist in 1661 was a manifesto for a new way. He rejected the qualitative element theory based on experimental observation.
Out with the old elements.
Pretty much. He argued for a particle-based view where chemical changes were explained by the motion and interaction of particles, a mechanistic approach strongly influenced by Galileo and Descartes.
A particle view of chemistry.
Yeah, he showed that what we call elements should be defined experimentally as substances that cannot be broken down into simpler substances by chemical means.
So the mechanical revolution wasn't just about motion. It was also about matter itself becoming a collection of interacting particles, fitting into that same mechanical picture.
Precisely. It was another step towards a unified, quantitative understanding of nature, where changes in matter, like changes in motion, could potentially be explained by underlying mechanical principles.
Okay, so the stage is set. Copernicus removes the Earth from the center. Kepler describes planetary orbits mathematically. Galileo figures out earthly motion and inertia.
Right.
Descartes gives us a mechanical philosophy in the math. Huygens tackles circular motion, and Boyle gives us the particle view of matter, and then comes Newton, who pulls it all together.
The Newtonian synthesis. Isaac Newton's achievement in Principia Mathematica was unifying the physics of Earth and the heavens under a single coherent set of laws.
It wasn't just adding a new theory.
No, it was fundamentally changing the framework of science.
The same force makes an apple fall in the moon orbit. That idea.
Exactly that idea. He provided a single, unified framework for all nature by combining Kepler's precise description of planetary motion with Galileo's insights into earthly mechanics, all within a powerful mathematical system. Newton showed that the entire cosmos operates under the same universal rules. It established the universe as a single, law-governed system.
And he went beyond just describing how things moved.
This is key. Kepler's laws described the how, Galileo described the how, Newton provided the why.
The cause.
Yes. He gave the causal dynamical explanation for why planets move in ellipses, why projectiles follow parabolic paths. This shift from pure description to dynamical explanation was transformative for the scientific method.
And his universe was fundamentally mathematical.
Nature, to Newton, was a vast mathematical machine. Its laws were not only discoverable, but they could be expressed with absolute precision in mathematical language.
So if you knew everything now.
Right. If you knew the initial state of the system, the positions and velocities of everything Newton's laws suggested, you could predict its future state perfectly. This is the birth of the deterministic view of the classical universe.
That sounds like a huge philosophical shift, not just a scientific one.
Oh, absolutely. Newton introduced concepts like absolute space and absolute time existing independently of anything within them.
Which was radical then.
Totally radical compared to views that saw space and time as defined by the relationships between objects. It sparked huge debates. Causality itself shifted from Aristotle's notion of purpose or inherent tendencies to a purely mathematical relationship described by laws and forces.
And this all culminated in his Principia.
Philosophia Naturalis Principia Mathematica, published in 1687, it laid out his laws of motion and universal gravitation. It was more than a book.
It was a blueprint.
Yeah, a blueprint for physics for centuries, a model of rigorous mathematical science. It was a whole new way to see and study the world.
To really understand Principia, you have to understand the man, Isaac Newton, and what shaped him.
His life is as complex as his physics. Born in 1642, the same year Galileo died. His father died before he was born, and he spent time separated from his mother.
And that affected him.
Some historians link this to his leader personality. Intensely private, secretive, almost paranoid about his work being stolen or criticized.
He went to Cambridge at a time when it was still quite Aristotelian.
The official curriculum was still steeped in the old ways, but Newton, on his own, devoured the works of modern thinkers like Descartes, Galileo, and Kepler.
Taught himself, basically.
Pretty much. He taught himself the cutting edge of natural philosophy and mathematics, developing his own deep interests.
He stood on the shoulders of giants, as he famously said.
He did, citing figures like Galileo for mechanics and experimentation, Descartes for the mechanical worldview and mathematics, Kepler for planetary laws, and Boyle for the particle nature of matter.
But his relationship with Descartes was tricky.
Yeah, it's worth noting his relationship with Descartes' work was complex. He built on the mechanical ideas but rejected the relational view of space and time. Led to big debates later.
And then came his extraordinary miracle year.
1665, 1666. The Great Plague closed Cambridge, and Newton retreated to his family home in Woolsthorpe. In this isolation, the dam broke.
What did he do?
He made foundational discoveries in optics, began developing his ideas on calculus, and crucially for our story, started formulating his ideas on gravity and the laws of motion. It's astonishing how much foundational work he did in that short period.
So the ideas for Principia weren't a sudden lightning bolt in 1687. They'd been brewing for a long time.
Absolutely. His secretive nature meant he likely worked on these concepts for years before showing them to anyone, constantly refining them.
His personality shaped the science.
His personality, both his genius and his protectiveness of his ideas, is integral to understanding his scientific output and his reluctance to publish.
He was also tackling questions that were already hot topics in the scientific community.
Right, he wasn't working in a vacuum. Scientists were grappling with fundamental problems. What exactly happens when objects collide?
Collisions, yeah.
How do you describe forces that aren't direct pushes or pulls? Was there a single force governing the cosmos? These were shared problems. Newton's genius was in his unique way of framing and solving them within a universal mathematical system.
Like the physics of collisions. That was a key starting point for his mechanics.
It was. In the mechanical philosophy of the 17th century, collisions were seen as the fundamental interaction matter hitting matter, transferring quantity of motion or momentum.
Descartes and Huygens worked on that.
Exactly. Descartes was big on this, and Huygens had done rigorous mathematical analysis of elastic collisions.
Newton started right there.
Yes, but he added something crucial. He introduced the concept of motive force, or vis impressa, an external force that changes a body's state of motion.
An external force.
Right. For Newton, in a collision, this force acted momentarily, causing a sudden, discontinuous change in momentum. Think of a punch, not a constant push. The change in the momentum vector is the result of this impressed force.
And this led directly to his famous laws.
You can see his laws as flowing from this analysis of how forces change motion. If there's no impressed force, no collision, no push, the motion doesn't change. It stays uniform in a straight line.
First law, inertia.
Right. The change in momentum caused by the impressed force is proportional to that force and in its direction.
Second law.
Second law. And when two bodies collide, the forces are mutual action and reaction are equal and opposite.
Third law.
Third law, which implies momentum is conserved in the collision.
So his laws provide the mathematical language for how forces, understood as causing changes in momentum, operate, especially in interactions like collisions.
Exactly. He took the existing conversation about mechanical interaction and formalized it with new concepts like impressed force acting over time, impulse, and rigorous laws governing those changes.
After collisions, the next piece was understanding curved motion, right? Building on Huygens' work.
Yes. Huygens had figured out the relationship for the force needed to keep something moving in a circle, the centripetal force. Newton independently arrived at similar results.
And his analysis was based on inertia.
It's beautifully simple from Newton's perspective. An object wants to move in a straight line.
Inertia again.
Right. It's moving in a circle. It's constantly being pulled away from that straight line path towards the center. This constant deviation from a straight line means its momentum vector is continuously changing direction.
And changing momentum needs a force.
Exactly. That continuous change requires a continuous force.
So the same kind of motive force, but acting continuously rather than suddenly.
Precisely. Newton saw the centripetal force as the same type of force as the impressed force in a collision. The difference was just in its mode of action, continuous change in direction versus sudden change in magnitude and/or direction.
That's a key generalization.
It is. This idea of a force continuously pulling towards a center was crucial for tackling orbits.
So he had the laws of motion and the concept of a central force.
Right.
How did he connect that to Kepler's laws of planetary motion?
Kepler's laws were incredibly accurate descriptions of planetary orbits, particularly his third law, which links the time a planet takes to orbit, period t, to its distance from the sun, radius r. T squared is proportional to r cubed.
Told you how they moved, but not why.
Right. Newton used his second law, EFMA, and the math of circular motion.
Okay.
He knew that for something moving in a circle, or approximately a circle for simplicity, the centripetal acceleration towards the center is related to its speed and distance. A is proportional to v squared over r.
V squared over r.
Got it. He also knew the speed v was related to the distance and the period. V is proportional to r over t, so acceleration is proportional to rt squared divided by r,
Which simplifies.
simplifies to r over t squared.
And here's where Kepler's third law comes in.
Exactly. Kepler's law says t squared is proportional to r cubed. Newton substituted this into his acceleration formula. A is proportional to r divided by r cubed, which simplifies too.
0.1 over r squared.
So the acceleration of a planet towards the sun must be inversely proportional to the square of its distance from the sun.
Wow. And since force equals mass times acceleration,
The force exerted by the sun on the planet must also be inversely proportional to the square of the distance. F is proportional to 1 over r squared. That was the monumental discovery.
linking Kepler and his own laws.
By combining Kepler's observational laws with his own fundamental laws of motion and math, Newton derived the mathematical form of the force causing planetary motion. It's an inverse square law.
And his biggest conceptual leap, showing this applied everywhere, on Earth and in the heavens.
Absolutely game-changing. Before Newton, gravity was seen as something specific to Earth, making apples fall. Newton showed that the same force, governed by the inverse square law, was making the moon orbit the Earth and the planets orbit the sun.
How did he prove that? Or, well, demonstrate it?
He calculated what the acceleration due to Earth's gravity should be at the moon's distance if it followed the inverse square law derived from Kepler's laws. He knew the acceleration of gravity on Earth's surface. He knew the ratio of the moon's distance from Earth to Earth's radius. If gravity followed the inverse square law, the acceleration at the moon's distance should be g multiplied by the square of that distance ratio. But inverse, Earth radius divided by moon distance squared.
And the numbers worked out.
His calculations showed that the acceleration required to keep the moon in its orbit was almost exactly this predicted value.
That must have been a jaw-dropping moment. Confirmation.
It was powerful evidence that Earth's gravity wasn't just a local phenomenon. It was a universal force extending into space and governing celestial motion.
And other evidence.
He also pointed to things like the tides caused by the moon's gravity on Earth and the subtle gravitational tugs planets like Jupiter and Saturn exert on each other as further evidence that gravity is universal.
And his shell theorem simplified the calculations greatly.
Yes, a brilliant mathematical proof. He showed that for a perfectly spherical body, the gravitational pull on anything outside it is the same as if all its mass were concentrated at its very center.
Which makes the math doable.
Absolutely. This made applying the inverse square law to things like planets and moons mathematically tractable.
So the conclusion, gravity isn't just earthly or just heavenly. It's between any two massive objects.
The profound concept of universal gravitation. Every particle of mass in the universe attracts every other particle of mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. F equals gm1m2 over r squared.
The famous equation.
That single law unified the cosmos and provided the framework for understanding everything from falling stones to orbiting galaxies.
We've touched on Edmund Halley's famous visit, but his role in getting Principia out the door was even bigger, right? He was more than just the guy who asked the question.
Halley was absolutely critical. He wasn't just a question poser. He was a champion and facilitator. He recognized the immense importance of Newton's work on planetary motion.
So when Newton mentioned the ellipse calculation,
Halley didn't just nod. He actively encouraged Newton, a notoriously reluctant publisher, to write it all down.
he really pushed him.
He did, and then some. Halley took on the responsibility of funding and overseeing the publication of Principia himself, even when the Royal Society was low on funds.
Wow, he paid for it.
Yeah, he edited it, saw it through the press, and helped introduce it to the scientific world. Without Halley's persistence and support, Principia might have languished in Newton's notes or at least been significantly delayed.
Okay, one of the most philosophically difficult aspects of Newton's gravity for his contemporaries was this idea of action at a distance.
This was a huge sticking point for many. Descartes' philosophy, for example, insisted that forces had to be transmitted by direct contact, like billiard balls hitting each other.
Or through that ether stuff.
Right, or through a continuous medium like his proposed ether. The idea of one object influencing another across empty space with no physical connection was deeply unsettling.
And Newton himself was uneasy about it.
He was. He couldn't explain how gravity worked its way across the void. He famously said he wouldn't propose hypotheses non-fingo about the cause of gravity. Describing how it acted mathematically was enough.
But he felt it needed a mechanism.
He admitted to Hooke and others that the idea of action at a distance without a medium was unthinkable and maybe even superstitious. Philosophically, he didn't like it.
So despite his philosophical discomfort, he put it in Principia because the math worked.
Precisely. He treated it as a working mathematical principle because it accurately described the phenomena, even if he lacked a mechanistic explanation for it.
Which was a new way of doing science, almost.
It was. This pragmatic approach, prioritizing mathematical description and empirical accuracy over a complete philosophical explanation of the mechanism, was itself a significant step in the development of science.
And while the mechanism remained a mystery, this idea opened doors.
It did. It showed that you didn't have to explain how a force was transmitted via contact or a medium to formulate a powerful predictive theory based on that force's effects.
Paving the way for later ideas.
Exactly. This paved the way for later concepts like fields in the 19th century, which provided a different way to think about influence across space without needing particles bumping into each other, eventually leading to Einstein's view of gravity bending space-time itself.
Let's quickly touch on the relationship between gravity and mass, which Newton's experiments clarified.
Newton did precise experiments, notably with pendulums, showing that the force of gravity, the weight on an object, is directly proportional to its mass.
Its quantity of matter.
Right, that intrinsic quantity of matter. A more massive object weighs proportionally more.
And acceleration in a gravitational field is independent of the object's mass. Galileo's idea.
Exactly. Galileo had shown this for falling objects near Earth. Newton confirmed it and generalized it. A feather and a hammer fall at the same rate in a vacuum.
Why is that again?
Because while the gravitational force on the hammer is much larger due to its larger mass, its inertia, its resistance to change in motion, which is also proportional to mass, is also proportionally larger. So F equals ma means acceleration A equals F over m. And if F is proportional to m, then A is independent of m. The mass cancels out, essentially.
And applying his third law seals it for the universal law.
Right. The force between two objects is mutual. Object 1 pulls on object 2, and object 2 pulls on object 1 with equal force.
Action, reaction.
If the force on object 2 is proportional to its mass, F euro m, and we know its acceleration is independent of its mass, A is independent of m, then from F a euro, the force must also be proportional to the mass of the other body, object 1. F euro.
Okay, so it depends on both masses.
So the force must be proportional to both masses. F is proportional to times m.
Combine that with the inverse square distance.
And you get the full universal law, F m m euro RFS.
It's stunning to think about this journey you've just taken us on from a world rigidly separated into changing earth and perfect heavens, understood through qualities and required continuous forces, to a universe unified by universal mathematical laws of motion and gravity acting across seemingly empty space.
Newton's synthesis was, well, an unparalleled achievement. It provided a framework that worked, allowed for incredible prediction and technological progress, and unified the physical world in a way no one had before. It set the stage for centuries of science.
And yet, as you mentioned, even within this brilliant framework, there were seeds of future revolutions.
Definitely.
The mystery of action at a distance, or the emergence of concepts like energy, heat, and electromagnetic fields later in classical physics, ideas that didn't quite fit the simple picture of point masses colliding.
All right, things like fields.
Hinting that reality had even deeper layers waiting to be uncovered.
It's true. The very success of classical physics opened up new questions and revealed phenomena that eventually required a new physics altogether. The journey from Aristotle to Newton was immense, but physics didn't stop there.
So thinking about this monumental shift, this move from qualities and separate realms to universal laws and a mathematical machine, what aspect of that transition, or perhaps one of those lingering mysteries Newton left behind, surprises you the most about how we've come to understand the fundamental nature of the reality?